Before we get into more complicated examples, we need to stop and make sure we understand the difference between a term and a factor. So I have two expressions here. On the left, 10 plus x squared, and on the right, 10x squared. So if we were to take the derivative of 10 plus x squared, the derivative of 10 is 0 because 10 is a constant here. It is a term all by itself. Remember, terms are separated with addition and subtraction, and so 10 is its own little piece right here. So this is a constant term. Its derivative is 0. And then when we take the derivative of x squared separately, term by term, in this case we get 2x. Now we'll compare that to 10x squared. Here the 10 is not a term. 10 is a factor. When we say that we have a factor, it means we're multiplying that number or that variable by something else. So in this case we're multiplying 10 by x squared. So the rule there says you have to take into account that factor into the derivative. So it gets incorporated because we take that power of 2 and we multiply it by the factor in front, the 10, and that all becomes part of the derivative. So the number 10 here is different depending on whether or not it's a term, like on the left, or a factor on the right. It's different in terms of the effect that it has on the derivative and the outcome. So keep in mind, a constant term has a 0 derivative, but a constant factor will become part of the derivative. So let's take a look at our next example. This is a polynomial multivariable function, 40x squared minus 10xy plus 5y squared minus 80. Notice the second term, negative 10xy, is what we call a mixed term. It has both an x and a y in it. So that's going to provide for us a little bit of a challenge, because when we take the partial derivative, one of them is going to be a variable and the other one is going to behave like a constant. So when we take the partial derivative with respect to x, what we want to do is rearrange that term so that it looks like some number, some constant in the front, multiplied by whatever is left over that includes an x. So the 10 certainly is a constant factor. The y, because it's behaving like a constant if we're taking the partial with respect to x, is also behaving like a constant factor. So y and 10 together, when they're multiplied, are considered to be a constant. So we put them in a parentheses there to remind ourselves all of this is a constant. And outside of that parentheses, we put the variable piece, the x. The last two terms we don't have to worry about because they're not mixed terms, so we leave them as they are. So let's go ahead and start taking derivatives. We're going to do the three derivatives that are not the mixed terms first, and then we'll deal with the mixed term last. So we're taking the partial with respect to x. The first term, 40x squared, is easy. It's just like we saw back in topic 4 and topic 5. The derivative of 40x squared is just 80x. The next term that we're going to consider is the 5y squared term. Now remember, we're taking the partial with respect to x. So y behaves as though it's a constant. Therefore, y squared is also a constant, and 5y squared is also a constant. So that whole term, that third term there, 5y squared, is behaving like a constant for the purposes of derivatives, and therefore the derivative of that is 0. And of course the last term, that negative 80, is always just a constant. There's no variable there at all, so that of course has a derivative of 0. So now we go back to this mixed term. Imagine for a moment that you had negative 11x there. What would the derivative of negative 11x be? Be negative 11, right? What if it were negative 37.6x? What would the derivative be? It would be that constant, 37.6. So when you have a term that is essentially a constant multiplied by x, the derivative of that term will simply be that constant. So in this case, our constant is the expression 10y. So 10y times x has a derivative of 10y. So when we put all that together, our derivative is 80x minus 10y. And this is a formula that gives us the rate of change of this function p as x is allowed to change. We say the rate of change of p with respect to x. It allows us to change the x variable, we fix the y variable, and then we see what happens to the independent variable z. So now let's take the partial derivative with respect to y. Same function. Now we have to keep in mind here that if we're taking the partial with respect to y, then the other independent variable x behaves like a constant. So that second term, which is the mixed term, negative 10xy, the factor there that is changing is y. That's the variable. Therefore, the 10 factor and the x factor are constant factors. So we're going to rearrange that second term so that it looks like some constant multiplier multiplied by some variable factor. The way we do that is by putting all of the constant factors inside the parentheses. 10's a factor, x is a factor, they're both constant, and then leaving the variable portion, the y, outside, just like we did before. Now, let's go ahead and take the partial with respect to y. We'll do the three non-mixed terms first. 40x squared. The derivative of 40x squared is what? You should get 0. Remember, we're taking the partial with respect to y. So x is behaving like a constant. So therefore x squared is a constant. 40 times x squared is also a constant. That whole first term has a derivative of 0 because that whole first term is really just a constant. X is not a variable here. Now let's look at the third term, 5y squared. Remember, we're taking the partial with respect to y, so y is the variable here. So this is a normal variable term that includes a y. So the derivative of 5y squared from previous topics is just 10y. And then of course the derivative of negative 80 is just 0. Now the mixed term looks like some constant, negative 10x, times y. So if you have constant times y, the derivative is just that constant, and therefore the derivative will just be negative 10x. So if we put all of that together, then the derivative is negative 10x plus 10y. As before, this is the rate of change of the function capital P with respect to y. So y is allowed to change, but x stays fixed.